Atkinson. I'm the lead programmer for Team 1334. And today I'm going to be talking about omni-robots. And just before I start, did all of you guys go to a competition last year? No? You guys didn't?
We were there in 2009.
Okay. So you have been to a competition before? Okay. So, I guess the first question is, what is an omni-robot? When you go to the first competition, most robots that you see, but 90% of them are either what you call tank drivers or skid steer. That you have two sides, usually there's 3 or 4 wheels on each side. And you drive the sides independently, so your robot can go forward, you move both sides forward, go backward, or it can steer side to side. The purpose of an omni-robot is to add another dimension to your movement, so you can also move left or right. And so it gives you a lot more mobility because you can now move all around the field and also turn. And so there's a number of very creative ways of doing that. But the problem is they're usually more complicated to control because with a regular robot, usually it's pretty easy. If you have 2 joysticks, you just assign one joystick to the left side, the other to the right side, or you can get a bit fancier and use one arcade drive style joystick where it's left and right and forward and backwards. But omni drives are a lot more complicated because you have many other things to deal with. And so a quick outline of what I'm going to talk about. To start off with, I'm going to talk about the general kinematics of an entire omni-robot. This is the kind of the physics and math behind what makes an omni-robot do what it does. And so that's going to be applicable to any kind of robot that you might build. And then the second part, I'll be getting into the more specific kinds of what you do for any form of omnidirectional robot. That's an omni-device. Okay. So, before we get started, the theory behind omni-robots is completely rooted in what are called vectors. A vector is a mathematical idea, and it's, if you want to visualize it, it's an arrow pointing somewhere in space. And so there are 2 useful ways that we can describe this arrow. The first one is what are called Cartesian coordinates, and you've probably done this a lot in math class. You simply say there's an x-coordinate and a y-coordinate, and that's where it points to. But there's another useful way of measuring this vector, and it's called polar coordinates. And what you say is, okay, the vector has an angle, it's going in this direction, and it's going a certain distance in that direction. So you have a magnitude, which is what r would be, and an angle, which you usually call theta. And so because these are both useful, I also have this. If you're looking to try and program an omni-drive robot, the equations can sometimes be complicated, so if you want, I have a sheet here of all the equations if you want to grab them. Where are they? Yeah, there's a pile here. So yeah. Okay. So because both of these coordinate systems are useful, we need a way to convert between them. And so to convert to polar Cartesian coordinates is just a little bit of trigonometry. And then to convert back to polar coordinates, we'll use a diagram here. But also, something that isn't really common in math is what's called the a-tan2 function. And basically, on your calculators, most will have a button that says inverse tangent or tan -1. The problem with using that is it's called, the actual function should be called the arctan, but they just call it tan -1. The problem with that is the answer that returns, there's actually another angle that it could return, but it just chooses not to, and it assumes that you know about this second angle and that you're able to deal with it. And ATN2 just takes care of all that for you, and you don't need to worry about it. So if you want to convert between these coordinate systems, use the ATN2 function. It's present in programming languages. And also, the computer deals in radians, and the problem is that most people find it much more intuitive to work in degrees. So if you're comfortable working in radians, you can do work entirely with radians on your robot code. Or if you want to use normal people angles, you can do it in degrees. And for that, you need to convert between the two, so it's like that. And radians is just another way of measuring the angle that the computer uses for some reason. So, okay. So just like numbers, vectors can be added and subtracted. And adding and subtracting vectors is very easy to do if you describe them in Cartesian coordinates, because you simply add the x and y coordinates pretty much independently of each other. And geometrically, what this looks like is, if we were to add these two vectors together, it would look like we put them end to tail, and then the overall vector, which would be x plus y, which would be the green vector plus the blue vector, is simply drawn to the end of the chain. And subtracting vectors, the way that I think about it is, if we want to subtract the green vector from the blue vector, what we're really trying to find is a vector so that when we add the green vector plus the second vector, we get the blue vector. So subtracting vectors looks kind of like that. It's like you put the vectors tail to tail and then connected their ends.